Hi everyone. Welcome back to this SystemVerilog Clocking Blocks session. In the today's session, we will look into more details of clocking block. If you remember, in our FIFO test bench, we had used the clocking blocks for driving the push interface as well as a pop interface, and we were using the synchronous FIFO, so we were using a clock, and then the write data, everything was, and even the full on the push side was sampled and driven using the clocking block. But at that point of time we didn't really worry about as to why are we using the clocking block, right? So we didn't worry about that, and in this session we will understand more details about the clocking block. Okay, and one thing I want to tell you is the clocking block is one of the constructs that relates to the low level hardware handling, right? So in the system Verilog, when we build the test benches, there are some constructs that help us interface with the design, right? And like we have the top level test bench module, we have interface, we have the clocking block is one among them, and subsequently for checking the low level interface signal waveforms we will be using the assertions, right? So interface, clocking block, assertions, they help us deal with the signal level activity or the signal level interface within the system Verilog to interface with a Verilog DUT, right? So we will look into them sort of as a unit, and let's today look into the clocking block. So in the today's agenda, what we will do is the first we will understand what problem are we trying to solve with the clocking block, right? And that is the and then as a part of that, we will encounter the race problem again. We have briefly seen about the races in our scheduling semantics session, but we will do a brief refreshing over here in the context of clocking blocks, and we will revisit this section or revisit this problem as to how it affects the problem that clocking block is trying to solve, right? In that context we will revisit the races, and then we'll understand what's really the clocking block, like a formal definition of it. I know we have already used it, but let's understand formal definition of clocking block, because our usage was very limited. We have not fully utilized the capabilities of clocking block, so we will understand what is clocking block and what are the features that this particular construct provides, and then how the skews are defined for both the input as well as output, and then we'll look at one more test bench use case, and then we'll close the session with some of the guidelines for the usage of clocking block. Okay, we'll start with this sampling and synchronization problem. This is a very important problem to understand in order to appreciate what the clocking block is doing, right? Let's take a simple design where I have two flops connected back to back, and what I'm doing is I'm just driving two over here at the input of the first flop, and I'm calling this output or the intermediate connection between the flop 1 to flop 2 as X, and then the output of second flop as Y, right? And how this particular design is expected to function, I just put it on a table over here, and so I am describing the outputs for these particular signals in the first column, and the second column is on the clock edge 1 what am I expecting on these outputs, and on clock edge 2 what I'm expecting, right? So on the on as soon as we come out of reset, of course both the outputs would be 0, and on the clock edge 1, right, that is post reset I'm talking about, the value 2 would come out on this output X, right? Whereas the post reset value of 0 would enter into the flop 2, and the Y would still remain 0, right? And on clock edge 2, the X will continue to have the value 2 because this input is tied to a constant value, and the Y should also see the value 2, right? This is a very simple circuit and a very simple output, right? Now let's look at in terms of when we want to simulate this circuit, what is a clock event, right? A clock event is a movement in your simulated time, and at that particular moment what is supposed to happen is the storage element values are sampled, right? Like for example, the D value over here is sampled and the D value of the second flop are sampled, and then at the same time the value of Q is getting updated, right? So now what is happening is, like, if we take this value X or the connection between flop 1 and flop 2 at the right particular edge of the clock, this output is also getting updated and this input is also getting sampled, right? And now when we are doing the simulation, right, if we are sampling and storing at the same time, how should this work, right? Because if it happens to sample the latest value and then immediately the value at the output of Y will also become 2 on the same clock edge, right? So it has to first sample and then update the value, right? That is the way it has to work. But this is a problem in simulation, but in real hardware this is not a problem, because anyway you have a clock to output delay, right? And then you also have a setup delay, so you have a real delays because of which this sampling problem, that, like for example, should you be updating the sampled values or should you be sampling first, right? That problem doesn't arise, right? But in the simulation we need to take care, right? And this is the problem that in the when we are implementing the SystemVerilog simulator, what can happen is, when I model these flops in certain ways, there can be cases where the determination means whether the storage will be sampled first or whether the storage is updated first, right? Can become, like, can vary, right? And sometimes it could get sampled and sometimes it could get updated, and because of that there exists a non-determinism, and that non-determinism is called as race, right? Let's look at an example to understand that further. There are different form of race conditions, and here let's look at read write or a write read type of a race condition, right? And what we are doing over here is, we had seen this particular circuit, and to understand that, should we be updating this output or should we be sampling this input, right? And what happens if there is a difference in the ordering of doing those actions. We were trying to understand that. Now let's say if I model this particular circuit in this way, that is, at always pause edge of clock, I have this always block 1 where I'm saying X equal to 2, and again I have always at pause edge of clock, and I have an always block 2, and I am just saying Y equal to X, right? So I am doing this now. How does this work, right? Now when I so now according to the LRM, now when we have these two always blocks, we know that both of these could be scheduled in any order, right? The ordering of the execution of the always blocks that we have, there is a indeterminism, right? There's no guaranteed order between them. So now if at the clock edge 1, if the execution order happens to be the always block 1 followed by always block 2, then what will happen is the value of X would get sampled to be 2, and then the same, because it's a blocking assignment I'm doing over here, the value of X will be available, and then Y equal to X, so the value of Y I'm going to see is 2. So this is the output I will see, whereas according to my modeling, I was expecting, if I were to model this hardware, this is the behavior that I was expecting and this is the behavior that I am getting, right? Now again, at the same time, if no, so there is this difference of output that is happening. That is one problem. The second problem is that on the same clock edge, if the ordering suppose happened that A2 executed first and then A1 executed, then the Y will sample the previous value of X, which would be 0, and then X will still get a latest value which will become 2, right? Now even if I forget this specification for a moment, there is a difference that depending on the order of execution of these two always blocks, the output result that I am going to see can be different, right? And this is the this indeterminism is nothing but the race condition. So this is what is the problem of race. Now the race condition that we saw in the previous slide, right? It's not just limited to like a RTL design. The same race condition also manifests when we are interacting from test bench to DUT. Here I'm just showing a simple DUT where I'm doing at passage of clock. I'm saying V equal to A plus 1, and then I have a test bench over here. I'm instancing the DUT, and then I have the variables to interact with the test bench variables to interact with the DUT, and I'm saying at passage of clock, and I'm assigning A equal to 1, right? Now here also we have the same problem. Now whether this initial block will get scheduled first, or will this always block get scheduled first at the beginning, right? And depending on that, beginning in the sense at the passage of the clock, right? So at the passage of clock, who is going to execute, right? Both of them would be blocked, but once the event on the passage of the clock comes in, who would execute first, right? Then again we have the ordering indeterminism, and hence now what value the B will get can vary, right? So this is the way there is a problem of indeterminism that happens also between the when the interaction takes place between your test bench and DUT. So let's just define the race further. So race condition is not a real hardware problem. Okay, race condition is actually a simulation modeling artifact, right? So that the way we are implementing the simulation algorithm, the simulator algorithm, the artifact of that, right, as a side effect of that, we are getting a race condition, and this race condition is happening because the execution between two different constructs, the order of execution, right, that we cannot guarantee that, and because of that indeterminism, that since we don't know in what order they are going to execute, any dependencies between them is leading to a different set of results, right? And the most common race condition is where you have multiple processes and they are trying to read and write a same variable, right? This is an important condition. So we saw that, right, between the two flops or between the test bench and the DUT, there was the same variable that was being driven, as which means that we were writing it and then it was being utilized at some place, right? So we are driving it as well as we are trying to utilize it. So that is where you will get the and happening at the same event region, right? That at the same clock edge you are trying to update a value and you are trying to also consume it and use it, and it's a very natural condition that's going to happen both within the design as well as between the test bench and the design, right? So what happens is, since the system Verilog doesn't guarantee the order of execution between these reading and writing processes, we don't have a way to know whether the read captures the old value or the new value, right? And that is the problem, right? And what we have to note is, although we will study the program block in future, we claim that the program block will solve all the race problem. This race problem that we are talking, it exists within the program block as well, right? This is the problem that exists both in module as well as within the program block, right? That's why UVM doesn't really use the program block. Now the certain type of assignments or expressions, right, which are scheduled to be scheduled in the same region, their order of execution is not guaranteed, right? So this means that they can change from time to time, and this change can happen, the change in the values that we see in the output can happen when we simulate it again and again or across simulators, right? So this non-determinism is finally what is the problem of race. So we said that certain type of assignments which are scheduled to be executed in the same time region. So let's look at few more examples to understand this further. I mean, we have already seen one read write or write read race condition in the previous slide. So let's look at one more. Here we have an initial block and we have an always block. This is a simple let's say if we did the clock generation modeling in this particular way, now what happens is that for this always block to work, the clock variable value has to be initialized with a value 0. Now if there is a race or the indeterminism that this always block gets scheduled first, then it may so happen that you will get X on the clock, because it will start with the undetermined value. So that is something that can happen. And then we have write to write race condition, wherein I am assigning two variables. I am assigning a single variable with the two always blocks. Now depending on which one executes first, the value of X can be different, right? So the point that we need to notice is the indeterminism, right? And then we have like a declaration and initial block, right? So depending on, so this also there is a like, whether the initial block gets executed first or your declaration based initialization gets executed first, there can be a race. And so the value, depending on the order, the value that gets initialized could be different, right? And then we have a fork join block race, wherein we have an event and we are doing a fork and we are triggering the event, and then in another block we are waiting for the event. Now depending on the order in which, this is also a block, there's no begin and end, but this is also a block. Depending on the order in which these two gets scheduled, there can be a possibility that the event has been triggered and this block was not scheduled, and then this could just get blocked, and the event caught display statement may never get displayed. All right, this can also happen. So this is a different ways in which the scheduling order changes, or the scheduling order indeterminism can lead to a different behavior, which is non-acceptable, and that is the essence of race condition. And the solution to solve the race problem is, one way is that we move the either reading or writing of that variables to a different event region, right? And we will look into it more details. And the most common way to do this is that we use non-blocking assignments. The non-blocking assignments indicated by this one, right, like less than, and then we have a equal to. So with this non-blocking assignments, and that's generally you would have read at many places that why non-blocking assignment is emphasized in the case of RTL design for writing to a particular variable. And what happens when you do this non-blocking assignment is that it postpones the update of the value of the variable on the LHS to a later region. And how that helps is that every time that when we use a non-blocking assignments, we are guaranteed to get a old value of that variable regardless of the order in which we execute. And we will see this further as to how this happens with the same example that we had seen before. We will look into it. And this is the technique that the RTL designers have been using, and that's why you would have probably read it in many coding guidelines for RTL coding. If you would have read that you have to use the non-blocking assignment when you are doing the RTL design. And this same problem can solve even the test bench race that we saw for the previously one. If we had used non-blocking assignments, it could solve. But for test bench, there are different options as well, that we can use a different clocking event. That is, we can use a negative clock edge for let's say sampling or driving from the test bench, and then a positive clock edge anyway the design is driving and sampling. And we can use also the clocking block, which we are going to study to offset this reading and writing problem from a synchronous edge. So we can use the clocking block as well to solve the problem in the test bench. And we will see, let's understand this first, that how does this sampling of old value and moving the time region helps. So this is the scheduling semantics of the Verilog 2001, which we had also seen it in our scheduling semantics session. So we have a previous time slot. I'm just quickly refreshing, and we have the current time slot, and the current time slot is made up of these regions. So we have an active region in which we were executing the blocking assignments, and since all the blocking assignments were getting executed in the active region, the latest value was reflecting, and because of that the dependencies were leading to the indeterminism. But when we use the non-blocking assignments, what happens is in the active region we only evaluate the RHS side of whatever that we are assigning gets evaluated, but it doesn't get assigned, right? And the assignment of whatever we have evaluated on the RH side to the LHS happens only in the NBA region, right? Now this is the key difference between when we are using the blocking assignments versus the non-blocking assignments. If we are using blocking assignments, all the evaluation as well as the assignment would have taken place in the active region itself, whereas when we are using the non-blocking assignments, the evaluation of the RHS is taking place in the active region, but the assignment of the RHS to LHS is not taking place in active region, but rather it's taking place in the NBA region, right? Now how does this help? So if we revisit back the same example, and we, let's say this is the way we had modeled using the blocking assignments, and the top table is what we were expecting as a hardware behavior. And let's say now if I change from this left side to the right side, right, that is from the blocking I'm changing it to the non-blocking. Now what happens, right? So now the in the particular time step when the passage of clock takes place, right, at that moment we are going to execute all the time steps that we talked about. So in the active region of this passage of the clock, the value 2, right, gets sampled and gets scheduled for the assignment in NBA region for the variable x. It's not assigned, but it's just sampled and scheduled, right? And in the while we execute this always block A2, again the value of x gets sampled, right? Now the value of x that we are sampling over here will be the previous value, and let's say if we are immediately coming out of post reset, the value of x would be 0. So we are sampling the value of 0 and scheduling it for assignment to the y. So in both the always blocks, any order they execute, right, we are not doing the assignment, right? We are just sampling the values. So what we will do, we will sample the value 2 in the active region and schedule it for assignment to the x, and we will sample the value of x over here, which will be currently 0 because this assignment has not taken place. We have just scheduled it to be assigned in NBA region, and while we are still executing it in the active region, so in the active region the current value of x would still be 0, let's say immediately out of the post reset, and that is what we are scheduling it for the y. So irrespective of the order in which this takes place, the value scheduled will remain same, and hence the behavior would be that on the clock edge 1 I will always guaranteed to get this behavior, right, irrespective of the order in which they execute. Since we just sample it and we do not do the assignment, the value is guaranteed to be deterministic irrespective of the order of execution, whereas in the blocking, since the value reflects depending on the order, because both the assignments are taking place in the active region itself. So if let's say x equal to 2 gets executed and then y equal to x gets executed, the y equal to x will see the latest value, whereas if y equal to x gets executed first, then the y will end up sampling the previous value. But whereas in the case of non-blocking assignment, since we just sample and we don't schedule, and then the actual assignment gets scheduled only in the NBA region, we will always sample the older value, and that's how the NBA region concept solves the race issue that we were seeing in the previous slide. So in the previous solution, we saw it in the context of RTL. Now in the context of the DUT and TB interaction, so we have changed all the assignments to non-blocking assignments. So we can use the NBA for both the RTL as well as for the TB. Now irrespective of the order in which the initial block or the always blocks get scheduled when the passage of clock comes in, there is no race problem, because we are just going to be sampling the old values and then we will consistently apply it irrespective of the order, right? And I would like to repeat that the real hardware will not have this problem, because there is always a propagation delays, and those propagation delays will prevent the the simultaneous reading and writing, because there's always a clock to output delay and a setup delay, right? So that will definitely prevent the same value propagating to the outputs, right? There's no problem that happens when we are doing it with the real hardware. And we can also, in the case of test benches here, we can use the negage of clock for driving. If you want to really use a blocking type of an assignment, you can use a negage of clock, and that will also still solve the problem. So if you use NBA, then it is anyway not a problem. But even if you are using a blocking assignments, if you use a negage, then there is no problem, because the race comes when you are trying to do a common variable read write on a same event, right? So for now what you are trying to do is a break that same event to a different event. When you do it on a different event, if you assign and read a common variable, so you're writing on one type of an event and reading on another type of an event, then also there is no problem of race. All right, so that is the basic idea. And all of these problems and solutions that we have already seen is what forms the motivation for the clocking block. And clocking block essentially uses the same ideas and creates a construct in which the user doesn't have to worry about it. So let's look closely as to what happens in the real hardware. A clock edge in real hardware is not just a single moment, it's a region. What do I mean by that is, if some information is coming in which needs to be sampled, it needs to be available TSU time before the clock edge. And if we drive some information on this particular clock edge, it's going to appear only after T clock to output delay, right? It's only going to happen around the clock edge and not exactly on the clock edge. Now if we model the same behavior in our test bench, let's say we have these two signals, which are same signals, we have from DUT and to DUT, and from DUT is driven from DUT and is coming into the test bench. So let's see how we can model it. So what I'm going to do is, I'm going to create a delayed version of it. So I will do a non-blocking assignment, and I'm taking a delayed from DUT as my target, which is on the right hand side, the left hand side, and on my right hand side I have from DUT, and I am using this delay operator. What this means is a postponed assignment, that is, as soon as the change happens, the value of this particular signal will be sampled, but it will be assigned to delayed from DUT only after TSU time. And this TSU and TCO can be parameters over here. Okay, now when the passage of a clock takes place, what's happening is this TB observation signal, I am doing a blocking assignment so that it becomes immediately available. I am doing a delayed from DUT signal assignment. Now if this signal had changed T setup TSU time units before the clock edge, right, and then the TB observation will be able to capture it, and if it has changed very close to the clock edge, then it will not be, I mean, if it is less than TSU, then this particular change will not be captured, and which mimics the real hardware behavior. And whenever we are driving, let's say the 2 DUT is the signal that we are driving, and whenever we are driving now with respect to this clock edge, we will create a 2 DUT signal which will be delayed by TCO, and we will be assigning the TB stimulus. So we have generated a TB stimulus and we are sampling it, but the value that we are sampling will appear on the 2 DUT, which is the actual signal that goes out to DUT only after the TCO. So this way, if we do it, then we are modeling a real hardware, and if we do it in this way, then the possibility of the sampling, I mean the possibility of the race that we were talking about, where like which one do we sample the value before or do we drive the value before, will be eliminated. And this is the the fundamental way we want to, there is a fundamental of your clocking block as well. But if we were not using the clocking block, this is another way in which we could have solved it. But if we did it this way, then the total number of signals that we are creating and everything can also become messy. So what we have done is, we have defined now a clocking block which mimics this particular behavior. So clocking block provides one place where all the thing that we did in the previous slide can all be specified, and the clocking block must be part of a module or an interface. It can be defined in a module or interface, and a clocking block specifies in one construct what's the clocking event that we are planning to use for the synchronization, the synchronization reference for the communication between your duty and test bench, and the set of signals that we need to sample or we are going to drive from the test bench, and any timing information, right? The TSU and the TCO that we talked about, it can all be specified in a single construct. And the way it's defined is like this: we have a clocking keyword, and we say simple CB, which is a name, at pause edge of the clock is the clocking event, and we are saying for this is the input signal, and the input skew is TSU from DUT. So any information that is being driven on from DUT will be sampled TSU prior to the point where it is being driven, right? Is sampled before that. That's the input skew, and then any information that we are driving on to DUT will be driven out on the actual signal only after TCO. This is what the clocking block specifies. In Verilog, we had only module as a unit of design entity, but in System Verilog, the same concept is extended to interface, which we have looked at that how it interacts with the rest of the design. Program block, which we will look at as to how it separates design from the test bench. Then there's a clocking block, which separates the clocking from the data activities, and where we specify the clock, timing, sampling and synchronization with the help of skews, and is mainly useful for the test benches. And the clocking block, similar to the module, has a static lifetime, and it has a scope local to its enclosing module, interface or a program. The clocking block only specifies the timing surrounding the clock events, that it specifies like relative to the sampling event, when the input signal needs to be sampled or when a particular value needs to be driven relative to the clocking edge, but it won't assign any values by itself. And assuming that like a clocking block is a part of an interface or module, the driving of signals which are present within the clocking block is a responsibility of its container. And that's why you will notice that in the future examples that we don't even specify the data width as a part of clocking block declaration. We only specify the direction. And one more point to note is, when we declare any interface or module, we create an instance of it separately, but whereas a clocking block, the moment we have declared it, there is an implicit instance that gets created with the same name, and hence the clocking block will be available to access with its container name dot the name of the clocking block. You don't need to instance it separately. As we have seen, even in the case of interfaces, it could be directly interface instance within the interface, or it could be through a mod port, but we don't need to again create a separate instance of it. As soon as we have declared it, it becomes available, and we can use the dot notation to access it. So let's understand few terms that will help us understand the clocking block further and make sure that the operation of the clocking block is clear. So first is clocking event. The clocking event is the one that is used to synchronize the clocking block, right? In this example, it's this pausage of clock, and it's known as a clocking event. And then there's a clocking signal, and the signals are sampled or driven. These signals are not the ones that we are actually referring in the clocking signals, although names could be same, but is the set of signals that ultimately get hooked up as a output port from the DUT to the clocking block signals, right? It's the actual signals are the clocking signals which actually get sampled or get driven. And clocking skew is the parameterized delay values. In this case, we have the input skew of TSU and output skew of TCO. And then there is this concept called clock variables, and these are the variables that we have declared within the clocking block. Now what happens is we have seen how the in terms of the clocking block that the signal gets sampled for the input TSU before the clocking event, right? So when we assign, or like when we read the values from the clocking variable, it is the responsibility of the clocking block to ensure that the clocking variable contains the value of corresponding signal which is TSU prior to this clock edge. And as well as when I drive the clocking variable, it's the responsibility of the clocking variable to drive out the clock variable value on the actual signal after T CO duration. Now if we put this whole idea in a form of a picture, it would look something like this. So we have the DUT, and these are your clocking signals to DUT and from DUT, and then they are connected to within an interface to your clocking block. And we have this synchronize and delay and sample type of an additional logic that's present within the clocking block. And a simple example of that we already saw in case of our the simple always block based how we could implement the clocking block functionality. The similar type of a logic which is present within the clocking block will take care of it. So whenever we drive CB to DUT through any non-blocking assignments in the test bench, what will happen is it will get driven to this clocking variable, and that variable will be synchronized to the clocking edge, and it will be delayed by the TCO that we had specified, and then it will be driven out to the DUT. And this is all the job that is done by the clocking block. And whenever we sample any signals through the clocking block, what will happen is it will delay that particular signal as we had seen, and then it will sample that particular value and then send it back to the DUT. And the delay and sample, the idea was that you are ensuring that if the signal has not changed prior to TSU, then only you are getting that particular information. So that is the idea if we represent it in a form of a picture. So here we are declaring a clocking block, and we are using the clocking event of clock 1, and then we are using a few input and the output variables. Now we can use this same clocking event and the same set of signals in multiple clocking block within the same container. There is nothing preventing that. If we have used a clocking event and variables in one clocking block, it doesn't prevent them from being used in the other clocking block. But every clocking block must be associated with at least one clocking event. That is very important. And then the skews, as far as skews are concerned, what we can do is we can define a default skew, and here we have defined with the input and output keywords. We have defined a default skew of 2ns for input and 3ns for the output. And this skew expression has to be constant. We can use the parameters, but it has to be constant. We cannot create a dynamic expressions over here. And once we have specified the default skew, then any input variables will inherit this skew, and any output variables will inherit this skew, unless we want to explicitly override it a particular signal. Like let's say if the data is a both in-out type of a signal, then we can specify an overridden value of input skew of 5 and output skew of 6 explicitly. So we can do this overriding, and the variables present within the clocking block, as we had already seen, we can be accessed with a clocking block name dot the name of particular variable. So this way you can access the signals present within the clocking block. The clocking blocks can be declared, as we have already seen, can be declared inside a module interface or a program. And let's say if I declare a clocking block CB at pos edge of clock, then I can just say at CB, and at CB means is equivalent to whatever the clocking event that I have specified. So at clocking block name is equivalent to the clocking event that we have specified for the clocking block. But the point is we should never mix the direct usage of the clocking event with at CB. So if you are accessing any of the information through if you are using a clocking block, and if you want to delay for few clocks, it's always advisable to use @CB, because if you mix these two, there is a scheduling region differences and that can cause some issues. So we should not mix these two. And scheduling, so if and in a particular module or a program block or an interface, if you have multiple clocking blocks, then any delay operations, it can become confusing as to which clock should be, like whenever we do double hash and a number specified delay, it can become confusing as to which clocking block should be used, and that can be explicitly specified. Either it could be explicitly specified, or you can set up a default clocking block, and default being a keyword over here. And if you set up a default clocking block CB, and then what will happen is that that specific clocking block clocking event will be used for the double hash delays. So let's look at the input skew. If in any of the clocking block, if the input skew is not specified, the default input skew is one step, and it's a special time unit. So what's special about it is that one step means like the time precision that we have specified. It's a 1 unit of the time precision that we have specified, and the signal gets sampled this 1 unit of time precision before the rising edge of the clock. And if you really go in the waveforms and see it, of course you will not be able to see it, not because of the time precision, but because there is no really separate signal within the clocking block which is visible, where we can see that the delayed signal. So that's not really visible, but this is how it works. And we can also think of one step as something that the input signal has sampled in their steady state in the time step immediately before the clock event, right? That's another way to look at it, that in the preceding time steps postponed region, you can think of it like that. So that is where your signal is getting sampled. We can also specify the input skew of #0, which would get sampled in the current sampling events observed region, and it's generally not recommended to use the #0 as your input skew, because that defies the purpose of the clocking blocks. So what is recommended is that you either use a default one step or a non-zero delay for the input skew. So the output skew from the clocking block, the default output skew is always 0, and we can also specify an explicit #0 skew. Generally not recommended, but it will then execute in the RE-NBA region of the scheduling during the time step. A non-zero skew is generally a good idea, because then the output skew, unlike the input skew, can also be observed in the waveform, and the time unit like PS or NS can be specified with the skew. And if you don't specify that, what will happen is in the module or the interface where you have, or the program block where you have placed the clocking block, whatever the time scale definition that is applicable to that particular scope, that time unit will be utilized for the skew. And I think this particular aspect is true both for the input skew as well as the output skew. So let's look at a test bench use case, and for any test bench use case, the clocking blocks are defined within the interface. As we had seen, even for the FIFO test bench, the clocking block we had defined within an interface, and the clocking block we had passed it to the mod port, and using that is how we utilize the clocking blocks in the test bench. And the signals declared within the clocking block, again we need not specify the direction of the same in the mod ports. And when we use the mod port, and we are passing a clocking block, then as we know, all the clocking block signals that we have specified become synchronous. So if there are any signals that needs to behave asynchronously, then we need to pass it separately via the mod port. So that is possible. So let's look at an test bench use case for the clocking block. So we are defining an interface sysbus INTF over here, and then we are defining a bunch of ports. and then we are defining this clocking block master CB, the clocking event being at pause edge of the clock, and then we are defining the skews, and the default skews, the input of one step and the output of #1, and #1 time unit will be derived from your time scale, and then we are declaring the signals that are the clock variables that are going to be used in this particular clocking block. And note that we are not declaring any data width, because the clocking block by itself wouldn't drive anything. And then we are defining a default clocking block over here, default clocking passive CB at pause edge of the clock, and we are defining the default input skew of one step and defining some of the ports. And by putting the default over here, what happens is, if I am declaring any properties, and if this property is sampling, would be using the default clocking block that I am defining over here in this particular interface scope. And then we are declaring two mod ports, and we are declaring a mod port master MP, where the clocking block master CB is getting utilized. And if you remember, as soon as we declare a clocking block, the corresponding instance of a clocking block with the same name gets created, so we are using that one over here. And then for any asynchronous signals, we are passing them additionally, so we are passing them as input. And then we are declaring one more mod port called passive MP, and then we are passing a passive CB clocking block, which is a default clocking block that we had declared over here. We are passing that, and then again we are additionally passing the asynchronous signal. Now this is the way we declare the clocking block and pass it to the mod port. And the way you use it is, like, let's say we implement a monitor and we want to use this passive clocking block. Then of course we will come in the UVM course. When we come, we will understand more about this UVM monitor, but for now let's focus on this clocking block. This will be the handle of your appropriate mod port, right? The one that's going to come into the 6 will be with the passive MP, that will be of the type, the instance of sync bus INTF instance with the passive MP mod port will be passed to this monitor, right? And then if I want to now monitor the signals present within this particular clocking block, then what I'm going to do is, for the clocking event, I am going to be directly using, you can note over here, @6.passivecb. So the name of the clocking block is used as a clocking event, and this implies implicitly at pause edge of the clock of this particular interface. And then for accessing any of the signals that are present within the clocking block, I am going to say 6 dot the passive CB, the name of the clocking block. 6 is actually going to come into this passive MP mod port, and then I'm going to say passive CB. So you can see that it has created a hierarchy, because it is static in nature. It has created a hierarchy, and then within the hierarchy I'm going to access the signals that I have declared within the clocking block, and utilize that information to do some processing. So that's how I will use it. So the two things, I am using the event from the clocking block, and I am sampling some information, and the sampling will of course happen one step, so that will be in the previous postponed region. The values will be sampled and utilized. And if you want to access the asynchronous signal, you can directly refer to the name of the mod port dot the name of the signal and equal to 1, so you can directly utilize it over here in your test bench. So in the previous example, we saw how we were able to sample the information from a clocking block, and in this one we will see how we are going to drive, and then how the double hash delays affect how does that affect when we drive it through the clocking block. For example, I will refer to a clocking block C, and this is the clocking variable. I am assigning to DUT non-blocking assignment with double hash delay of 5 and a new value. This is the postpone drive. Here what happens is, the new value gets sampled as soon as the statement gets executed, but the assignment to the 2 DUT happens after the 5 clocking events later, right? And then it will happen, so it will happen after the 5 clocking events, and the results will actually become visible on the signal after the the output skew. That's what will happen. And but if I do it with this way, that is, if I put the delay before the assignment, that is hash hash 10 and c to dut some value, then this will, the whole statement itself get executed after 10 clocking events, and after 10 clocking events, whatever is the value of second value, that will be sampled and it will be assigned to this c dot t to dut clocking variable, and the output from this clocking variable to the actual clocking signal assignment will take place after your output skew, right? So that is what will happen. So this is the difference, that if I'm using the delay over here, it will be sampled and it will do the delayed assignment, whereas here if I include it prior to the assignment, then it will delay the assignment itself, and once it delays, the latest value of the RHS gets sampled. So let's take an example. I have defined the default clocking block to be C, right? And I am assigning C dot to DUT. I am doing a postponed drive and I am doing a delayed execution in the second statement. And in the third statement, I am assigning a variable to a different clocking block, D dot, and the clocking variable is out variable, and I am doing another postponed assignment, postponed drive, and here I have defined now double hash delay, and this double hash delay will not use the default clocking block, but it will use the clocking block clocking event of D, right? It will use a clocking event of the D, because whenever we drive the variables through a different clocking block, the corresponding clocking blocks clocking event will be utilized. It will not use the default clocking block that is active. And by contrast, if you have any if you don't have any clocking default clocking block defined, and you try to use the double hash delays, that would be illegal, because the simulator wouldn't know which clocking event to use. And generally, one of the recommended practice is that to avoid this confusion, to figure out, okay, which default clocking event is active, and we are driving, and let's say, but the driving through this one we wanted a different clock based delay, so you can also implement like a wait for clocks type of a task, and in this task you can utilize the explicit clocking block delays, and avoid the confusion of using the hash delays, because this hash delays is dependent both on the clocking block being driven and the active clocking block being active through the default clocking block definition. So those confusions can be avoided. You can, if you use an explicit task where you can wait on certain clocking block events itself, so that will avoid that confusion. So here we have few guidelines for the clocking block usage that I picked up from a nice paper. I'll share that link to the paper. So whenever you are using the clocking block, there are two things that you need to take care, right? Do not bypass the clocking block. What does that mean is that do not assign the signals, the clocking signals, right? The ones that are connecting to the clocking block, do not assign to them. Always use the clock variables that you have declared within your clocking block, and don't mix them. And second thing is, you have defined a clocking event, so any waiting that you need to do for clocking events, you use it through the clocking signal, the name of the clocking block, rather than using the direct clocking event. You use the name of the clocking block event to wait, and for the output clock variables, whenever you are driving clock variables, whenever you are driving, you use the non-blocking operator. Do not use the blocking operator on the clock variables of the clocking block, as we have already seen the possibility of the race. And then you use for the input skew $1 step, unless and until you have some special reason, because this ensures that your clocking block is sampling it in a way very similar to the way your even the SystemVerilog assertions are sampling. because your assertion is sampling it in the preponed region, and the whatever the $1 step which we have talked about, that it uses one time precision unit, which almost equivalent to either the postponed region of your previous time step or the preponed region of your current time step. So that sampling will ensure you have a very consistent values. And use non-zero output skew values. There are two reasons. First is it's going to make your waveforms clearer, that you will be really be able to see when you see with respect to a particular clock edge, the output will show slightly delayed, so it will be very clear that what is a value that is going to get sampled, or the value got updated. It becomes clear to while you are doing the debug. And also sometimes what happens is when you are performing the gate level simulation, due to the clock network or your clock tree delays, if the clock gets slightly shifted and if you have the right output delays, then the value sampling will be correct. So that is another benefit that you get when you use the non-zero output skew values. And do not use, although you can specify input skew value of 0, it is not recommended to do that. That defies the usage of. So declare your clocking blocks in interface, and then expose the clocking blocks and any of the asynchronous signals through your mod port, as we have already seen. And in your verification code, you declare a virtual interface data type, and then while you are passing the interface to it, you pass it with the appropriate mod port to restrict the access. And then it's better to establish the, if you are planning to use a clocking block, better to establish the direction with respect to test bench in your clocking block, and then pass the clocking block to the mod port rather than adding the raw signals directly in the mod port, because when you do that, then they also become available to be driven asynchronously, and that can cause confusion. And clocking box should be accessed through the virtual interface, and you pointing to your mod port. And so the way it would generally become accessible is you use your virtual interface name, then the clocking block name, and then a dot clock variable. So this is the way to access, and should be followed across while driving as well as sampling, to ensure consistency, that you are not bypassing the clocking block or accessing it through directly through the virtual interface, and that can lead to confusions. So if you follow these guidelines, then the clocking blocks would provide you the the ability to specify all timing and synchronization information at one place, and then prevent race conditions. Um, so one final note that I would like to add over here is that there are times where you may not have a completely synchronous interface, and that within the same clock you might have to drive some of the signals, and there could be possibility of some asynchronous operations. And in those cases, sometimes the clocking block can become very restrictive. So you can define an asynchronous mod port to the set of signals that you intend to use asynchronously, and utilize that for doing the verification. And as long as you use the practices to prevent the race, you can still make things work. So the clocking block is one of the tricky areas to understand. I hope this session gives you the clarity as to how does it work, how do we need to declare it, and how do we need to use the clocking block, what problem is it trying to solve. So I hope that it gives you that clarity. Thank you for listening.